know the formula for a Simpson's rule summation for a numerical approximation to an integral, and we also know the formula that gives us the upper bound for the error due to that approximation. I want to make these ideas a little bit more concrete, so we're going to talk through a few examples to illustrate them. The first example is the integral from 1 to 2 of dx over x using two subintervals n equals 2. Now it's helpful to visualize it, so here's a picture of the graph of the function 1 over x, and we see the interval from 1 to 2. It's subdivided into two subintervals, so there are 3 points on the curve, and they correspond to the 3 values of y, y0, y1, and y2. And we also can see from this picture that delta x is equal to 1/2. With this information, we can now calculate the Simpson's rule sum. So the integral is approximately equal to delta x over 3, which is 1/6, times y0 plus 4y1 plus y2. So the pattern was 1, 4, 1. See, when you have 6 elements, then the pattern's 1, 4, 2, 4, 2, 4, 1. But when you have 3 elements, the pattern's 1, 4, 1. When we simplify this expression, the result is 25/36. And that is our n equals 2 Simpson's rule approximation to the integral from 1 to 2 of dx over x. Now let's see how much error we expect there to be in this approximation. We'll use this error formula. And first of all, we need to know the value of k. K is defined as the maximum magnitude of the fourth derivative of the function. The integrand here is 1 over x, so that's our function, and when we calculate the fourth derivative, we find out it's 24 over x to the fifth. So we need the maximum magnitude of 24 over x to the fifth on the interval from 1 to 2. 24 over x to the fifth is decreasing on that interval. The bigger x gets, the smaller the value of the fourth derivative. So the maximum magnitude occurs at the left endpoint of that integral, and we get k equals 24. So now that we know k, I'm going to plug into this formula. The error is less than or equal to k times b minus a to the fifth divided by 180 times 2 to the fourth, n to the fourth. And when we simplify this number, it comes to 1 over 120. So we have our two results, that the value of the integral is approximately 25/36, and that the error in that approximation is no greater than 1/20. We happen to know the true value, the exact value of the integral, so we can now check whether that worked. The 25/36 is 0.69444. If I write down the value of natural log of 2 and subtract it, then I get the exact error from the Simpson's rule sum. Is this number less than 1/120th? The error is less than 1/120th, so it did work as 1/120th did work as an error upper bound. Now, in the next example, we'll use the same function, but we'll ask a different question. Suppose we need to estimate this integral to 5 decimal places. We need to know that those 5 places are correct, or we happen to know the correct answer. So let's say we need to use the Simpson's rule approximation and get the number 0.69315, correct in all those 5 places. Well, this means that our error has to be less than 0.00001. If the error is smaller than that, then we have, to within 5 decimal places, the correct answer. And by the way, this is 10 to the negative fifth. So if we want our error to be less than 10 to the negative fifth, we set the upper bound to be less than 10 to the negative fifth. And then by the transitive property of inequalities, we have our error must be less than 10 to the negative fifth. Remember, we know the value of k already. It's 24. We computed that before. So when I substitute in k and b and a, I can take this inequality and then solve it for n. It's just simple algebra manipulations. You will need the calculator to compute the fourth root to solve for n. And we see that n must be greater than or equal to 10.7. if n has to be an even number, then that means the smallest value of n must be 12. So we set n equal to 12, and we know that if we use a Simpsons rule calculation using n equals 12, we are guaranteed to get the number 0.69315, correct to all of those decimal places. Now in our next example, we're going to try to compute this Simpsons rule approximation with n equals 12 and see if we get 0.69315. Let's start out by calculating delta x. We know delta x is 1/12, so delta x over 3 is 1/36. And the sum we want to compute then is 1/36 times this pattern, 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. That means we need to get these 13 values, y0 through y12, which means we need to divide the interval up into twelfths. It seems like a lot of work, and it might seem daunting. So let me go through the way you would do this if you have a TI-83 or TI-84 calculator. And take out your own calculator now and follow along, otherwise the steps won't make as much sense to you. I'm going to have you start out by pressing y equals and set up the function 1 over x to be in y1. So press clear to clear out whatever's in there, and then type 1 over x for your function. Once you have y equals 1 over x, press stat 5. Stat option 5 is set up the editor, and press enter. Now we have the correct list names in our list editor, and then press stat and option 1. And you open up an editor and you see a bunch of lists called L1, L2, L3, etc. Now the first thing I'm going to have you do is clear out these lists. Left arrow over so that you're in list L1, and then arrow up and press clear and press enter. And when you do that, you should see list 1 disappear. You've cleared out everything in list 1. Then right arrow over and clear out list 2, and continue, clear out list 3 and list 4. Once you've cleared out the lists, left arrow back over to L1. And now up arrow again, so you're up in the top of above the L1 column. And you see at the bottom of the screen there's a prompt, L1 equals. You're going to fill it in by hitting second list and then go to the operations menu and choose option 5. Option 5 is sequence. Sequence is going to generate a sequence. And the sequence we want is 1 plus j divided by 12. 1 plus j divided by 12. So first hit those keys, 1 plus j, it's over the comma, divided by 12. And let's stop here for a second and think about what that means. These are the values of x. X starts at 1, and it goes all the way up to 2, and the step size is 1/12 of a unit. Delta x is 1/12. So the sequence of values of x are x0 is 1, x1 is 1 plus a 12th, x2 is 1 plus 2/12, and so on. The sequence is 1 plus j over 12. We need to put a comma in now because this sequence command has multiple arguments. And the next argument is the name of the variable that is counting up. So hit alpha j, and then put another comma. And the next argument is the starting value of j, and then the next argument is the ending value of j. So comma 0, comma 12. After you have entered that and put the close parenthesis, hit enter, and you'll see that the list becomes populated by the 13 values of x. And just to check that this really is correct, scroll down to the bottom of the list and you'll see that the last element should be L1 of 13 and it should be equal to 2. Now we'll move on to list L2. So right arrow over to L2 and then simply type in the numbers 1424242424241. And if you've done this correctly, then your very last one should line up with the last element of list L1, which is 2. Now we're going to arrow over to list L3. And to compute L3, we're going to use calculations of the function that we stored in y1. So press var's right arrow 1, 1 to get y1. And then we need to tell it what values of x to compute y1. So put y1 of L1. Put parenthesis, press second function, hit the number 1 to get L1, close parenthesis. y1 of L1, in other words, evaluate y1 at all of the x coordinates and make a whole list of numbers. And these are the y values, which when you press enter, you'll see that the y values will populate the list L3. Now we have all the y values. The next thing we need to do is multiply them so that we have 1 times the first, 4 times the second, 2 times the third, and so on. In other words, we want to now make L4, right arrow, up arrow, make L4 equal to L2 times L1. L2 times L3. So press second 2 times second 3 and press enter. And L4 is now the actual numbers in this sum. We now need to add them up and divide by 36 to get our Simpsons rule approximation. So quit out of list editor mode and now choose list math option 5, which is sum, and we want to sum list L4, so hit second L4, which is second 4 on the keyboard, and then you want to divide the result by 36. And when you press enter, you should see the result of the Simpsons rule calculation. And if you round it to 5 places, you should get 0.69315. And did you get 0.69315?